All right, so now we move on to lesson 8 of polynomials, and it's factoring with difference of squares and perfect square trinomials. So we're going to begin this lesson by looking at what a difference of squares is, or a difference of two squares, and how we can factor these. So whenever we have some binomial, and each term is some square, or could be written with an exponent 2, and there's some subtraction sign in the middle, then we know that we have some difference of squares. So if we look at this, formally put, we have two squared terms and some subtraction sign between them. We know this is going to be a difference of squares. Now, how can we factor these? Well, let's go to the next page here. And if I look at example 1, we're going to work through this here. So is this a difference of squares, and how do we know? Well, we would want to look at each of the terms and see if they perfectly square and aren't irrational. So if I square root x squared, well, I'm left with just x. So that's definitely irrational. If I square root 9, that is equal to 3. That is a rational number. So it is a difference of squares because we have one perfect square subtract another perfect square. Now, how do we factor the difference of squares? Let's look at method 1 by inspection. So by inspection, we knew from previous lessons, well, if we have some trinomial, then we can see, oh, what multiplies to make our outside number and adds to make our middle number. So in order to make our expression we were given, x squared minus 9, look like a regular trinomial, well, we force it to have this negative x or negative 0x term in the middle, or positive 0x in the middle, because we know anything multiplied by 0 goes away and becomes 0. But this is a way to force it so that it looks like it has a middle term here. Now, we must multiply to make that outside number. So two numbers that will multiply to make the outside number of negative 9 and add to make 0 in the middle. Well, those two numbers would be negative 3 times 3. Because negative 3 times 3 definitely gives us that negative 9. And if I add a negative 3 plus a positive 3, well, this is equal to 0. So by inspection, we know because a is equal to 1, which I'll actually write above here, a is equal to 1, we can do inspection. And so by inspection, here's what our factors are. X minus 3, x plus 3 is equal to x squared minus 9. Now, we want to check our answer and see if this is actually our factored terms or our multiplied binomials. So if I take x minus 3 and x plus 3 and I FOIL them, well, here's what I'm going to get out of this. I have x times x and x times 3. That gives me equal to x squared plus 3x. Now I need to multiply negative 3 by x, negative 3 by 3. That's going to give me negative 3x. And then negative 3 times a positive 3 is negative 9. And then finally, what we should know about the middle is if you see these middle two terms, it's a negative and a positive version of each other. These cancel out. They go away. So I can cancel my two middle terms. They go to 0, and therefore I have x squared minus 9. So we've shown this binomial of the two factors expands back to my binomial here, or the difference of squares. Now let's look at example 2 here. They say 2x squared minus 72x, is this a difference of squares? Well, what I would do is I would first start by saying, okay, if I square root 2x squared, is this a perfect square? What you would realize is that as soon as you square root a 2, this is actually irrational. So something is a red flag here. What was always our first step of factoring? It's to remove a GCF. So we should look at 2 and 72 and say, is there something I can remove here? In this case, I can remove a GCF of 2 out front. So I'm going to say this is equal to 2. If I take a 2 off of both these or divide both of them by 2, I'm left with x squared minus 36. And now I can see if my terms, or my x squared and my 36, are perfect squares. So if I square root x squared, well, that's equal to x. If I square root 36, this is equal to 6. So yes, this is a difference of squares. Now, just as they say in number 2 here, how do we know it's a difference of squares? Well, we were able to expose this. How were we able to expose the difference of squares? We remembered that removing out a common factor, or our GCF, is always the step 1. And now, by inspection, we took out that GCF of 2, and our statement became from 2x squared minus 72, 2 times x squared minus 36. Now, by inspection, here's what we can do. So let's flip the page here and go to our next page. We now have our statement as 2x squared minus 36. What if I do what I did in the last problem and I assign a 0x in the middle, almost as a placeholder here for a regular trinomial? Now we need to multiply to make our outside term, or negative 36, and add to make 0. What two numbers can do this for us? Well, if I take negative 6 and I multiply it by a positive 6, that's definitely a negative 36. And if I take negative 6 and add it to a positive 6, this will give me 0. So by inspection, and just to furthermore state it, if we know that a equals 1 here, we can do factoring by inspection. So my two factors here are x minus 6, x plus 6. And now let's just double check our answer to see if we can go from our two binomials back to our difference of squares. So if I take our answer here, we have 2x plus 6 and x minus 6. And I know that's written in the opposite order of the one just above, but we can change the order. It doesn't matter if we have this order or the positive first. They are the same thing. If I FOIL this, I take my x and multiply it to the two terms in the next bracket. This is equal to 2 times x squared minus 6x. Now I multiply 6 times x, 6 times the negative 6. This is positive 6x. And finally, 6 times a negative 6 is negative 36. Now I combine the like terms. Here I realize I have a plus minus of the same term. Therefore, I can cancel these out. Stated as 0, and this is equal to 2x squared minus 36. Back to our binomial of difference of squares. All right, so there is another method or a shortcut available in order to factor a difference of squares. Do we notice the pattern from the previous? So if we looked at both of them, when we got it into our factored form, what did we notice? Well, it was the same number plus or minus for our factors. So in the first case, we knew the factors were 3, but it was positive and negative 3. They immediately go into the bracket. In the next one, we had negative 6 and positive 6. It was the plus minus of the same number. So if we want to formally state this, well, here's how we do it. We take the square root of the first term. So let's say it was x squared. Well, we get an x value. And if I take a square root of the second term, let's say that was 9, then I get 3. And therefore, we set up the binomial with a plus minus, and we always put our x and then minus whatever that first number was, and x plus whatever our factor was. Therefore, giving us x minus 3 times x plus 3, we expand this out, and we know when we expand a difference of squares, the pattern we saw was that the middle produced a plus minus of the same factor. Those go away. Plus 3, minus 3, they eliminate to 0, and therefore I would get this difference of squares, or a binomial of a squared term, and then a constant on the end that is also a perfect square. All right, so here's our general rule. The general rule for factoring a difference of squares is to say if I have two perfect squares, it is the plus minus of their square roots. So if I want to formalize this even more below, square root of x squared is equal to x. Square root of y squared is equal to y. So our factors are therefore the plus minus versions of each. Now order matters here, because if x comes first, x must come first in the two brackets or our two factors. If y is second, y has to come second if it was second in the binomial. All right, now we're going to shift a little bit and we're going to look at factoring perfect square trinomials. So rather than a difference of squares, now we have a traditional looking trinomial, hence an example like this, but we're going to get something specific as a result. So when we factor this trinomial by inspection, we're asking ourselves, okay, well, what multiplies to make 36 or the outside number, and what adds to make 12 or the middle number? So the two numbers that will do this for us are 6 and 6. So by inspection, because I know that my a value is equal to 1, the reason I can do inspection is a equals 1, I can throw these right into my brackets of x plus 6, x plus 6. And now what's a way to rewrite this in terms of if I want to write it as one binomial? Well, we know the same thing multiplied twice, we can write it as a squared. And we actually know this from exponents. If we take two things, let's say I gave you x times x. Well, two things that are the same multiplied together become x squared because we add the powers together and keep the term consistent. The base is the same, so we add their exponents. In this case, I could put a 1 and a 1 here. So x plus 6 to the 1, x plus 6 to the 1. We multiply these together, common base multiplied, we add their exponents. Okay, and now if it shares the same term, this is a perfect square trinomial, or if the factor is the same, it's a perfect square trinomial. Let's look at another example. I have another trinomial, or another traditional looking trinomial. What will multiply to make 25, or the outside, and what will add to make 10, or the middle? We would find that these two numbers are going to be 5 and 5. Because my coefficient a is equal to 1, we know that these can be put right into the factors, and something that's written the same multiplied together becomes x plus 5 squared. It's common base, we keep the base and add the exponents. Therefore, because it's the same factor, we know it's a perfect square trinomial. Okay. Now, they say to have a discussion on this, but we've pointed out all the important facts here. We know that if we have the same factor and a equals 1, or we know we can do inspection for both of these, then the factor will be the same, and we can write it as a squared rather than writing it out by two binomials. All right, and then a couple more ideas to discuss here. So both of these are known as perfect square trinomials, both of our examples on the previous page. So what are some characteristics of perfect square trinomials? Well, there's a couple different things here. If we know that is a positive perfect square trinomial, then the characteristic from the trinomial that we'll notice is that we'll have a positive for middle term. So if your trinomial ends up being a perfect square trinomial with a positive in the middle term, it will be a positive for your factors. Similarly, if it's a negative in the middle term and you find that it's a perfect square trinomial or shares the same factor, then you know it's going to be a negative in the middle of the binomial. So let's work on steps to discuss if this is a perfect square trinomial or how we can determine perfect square trinomials. So let's take the square root of the first term. So in this case, our first term is x squared. Perfect square becomes x. We take the square of the second term, and by second term, what they actually mean here is our last term. So if I square root 49, this is equal to 7. Now, I'm going to multiply the terms from step 1 and step 2, and then multiply it again by 2. So this is going to become 7 times x, which is equal to 7x. But then they say we need to multiply this by 2, so it's 2 times 7x, and that is equal to 14x. So what do we notice about this? Well, we know that this term we just discovered here, this 14x, is equal to my middle term. So if I square root my first and square root my last, multiply them together and then multiply them by 2, if that is equal to the middle term, then we have a perfect square trinomial. Now, I'm not a big fan of the formulaic approach like that and trying to figure out cheats and hacks behind these problems like this. I would rather you conceptually understand that if we're doing something by inspection, and you get the same factor, whatever that same factor is, it can be written as the binomial times binomial or the binomial squared. All right, make sure you're doing the practice problems and the check your understanding.